first image that pops up on Google when you search for neural networks? You know, how many of you remember Terminator from the 1980s? You do, right? A very good franchisee. I mean, now with part 5 and 6, it's terrible. But yeah, so neural networks as such is not a very new concept. It was developed in its present form. Every algorithm you see, it was developed in the 80s and late 90s, and that's when Arnold Schwarzenegger and team, they picked up the word neural net, made it into Skynet in their movie, where AI takes over humans and all. But one thing you have to realize is that it's a very broad field, and people tend to throw in jargons, and we shouldn't be scared of when people say AI, machine learning, deep learning. They use it interchangeably, but if you look at the actual thing, this is how it is. AI is a very broad field. Okay, it's like, are there any computer science students here? Like, anyone who had studied computer science algorithms? So there is this nice algorithm in graph search known as depth first search. Has anyone heard of it? Depth first search. So what depth first search basically does, you know the maze, right? A simple maze. Depth first search just solves the maze, and that's also AI. So AI has, the term AI has been there since the 1950s. First when John McCarthy, is known as the founder of AI, when he and his team proposed for a lab in the late 1950s. Since then, people have been using AI for various contexts. But machine learning is basically a statistical technique. It's from the field of statistics, but it does what AI is intended to do. Make a bot that takes decision based on data. So that is one of the ways to AI. So AI is very broad field. You have many ways to AI, and then deep learning comes under machine learning. Like in machine learning, you have various techniques. One of the technique is neural network, and the extensive study of neural network is another subject by itself known as deep learning. So this is the broad understanding of the field. Studying AI. Stay away from any AI related news in any website. I'm not even talking about BuzzFeed or ScoopWhoop. I'm talking about Times of India, BBC, and Guardian, because the press tends to like, they don't know what's happening, as they just tend to hype things up to get clicks. And so if you always read the original paper or blog before arriving at any conclusion, like how many of you remember this? Like around 4 months ago, there was huge news. Two bots inside Facebook, they were chatting along themselves in some language, and they had to shut it down. Well, if you go to the math behind that, that's like a very common problem. It's not a new language. It's just they were talking in mathematics, which we couldn't understand. So you separate the hype from AI, and you look at the mathematics behind it. It's fairly simple. It's intuitive. It's not there's no magic in it. And yeah, TED Talks are notorious for being misleading. I don't know how many of you have seen this. There's a very famous TED Talk where where the speaker presents a small drone, and he has a human figure there, and the drone comes and kills that human figure. Well, guess what? That was fake. And there is also this famous robot known as Sophia, right? It went to IIT Kharagpur. It was showcased in Dubai and stuff. The thing about that is it's not even close to cutting edge. Like most of the things that robot does is pre-programmed. So it's just marketing out there. So stay away from two sets of people. Like there's MBA marketing types who go on saying we have this, we have that, and journalists. Like AI is not about them, because this is what happened even in the 1960s when a very basic model was constructed. New York Times reported, oh, okay, the perceptron can learn. It can learn now. It's a conscious thing. We have hit AI. Like we have achieved sentience and stuff. But then the simple perceptron, as you can see later, I'll show you, it will fail to learn even the XOR function. XOR, right? If the signal is 1, it is 1. Otherwise it's zero. It fails to learn even that. So what happens is this unnecessary hype leads to unnecessary, expectations from the field, and when we cannot meet it, it leads to a funding crunch. So that's what happened even in the 80s, because of when the Hollywood took AI, people started thinking, oh, okay, we can expect a lot from this, but there is no computational power in the 80s, and they couldn't do much at all. And from the 80s, it's known as 80s to till the late 2000s, it's known as the AI winter, because no one wanted to fund for anything in AI because it is not a promising field at all. So yeah, these two people out there, Elon Musk and Zuckerberg. How many of you are Musk fans here? Like, you like Elon Musk? Okay, when it comes to AI, you shouldn't take him seriously, because he is more of a rocket scientist than an AI guy. And he says Zuckerberg's understanding of AI is limited, but I seriously doubt that, because Zuckerberg is a CS graduate from Harvard University. I mean, dropout, but I would say Mark Zuckerberg, despite his flaws, despite Facebook's flaws, he has a better understanding of what AI is. And when you look at, okay, so OpenAI, it was in the news actually, like in the last week. So how many of you played Dota here, the game Dota, or even, I think everyone has heard of Dota, right? It's a fairly famous game. So if you know, if you play Dota, you know it's not a simple game, because it's a 5-player game, like 5 versus 5, and there's a lot of strategy involved. Like, all the 5 players need to coordinate with each other, and you basically to destroy the towers of other player. That's how it is. Okay, it's a very complex game. And so last week they got the best 5 human players versus they trained bots using deep learning. They call it the Open AI 5, and we can watch the match on YouTube. The match lasted 18 minutes with the humans losing 3-0. So yeah, that's the power of AI. So yeah, coming back to this Elon Musk versus Zuckerberg, I would say it's not necessarily to follow any of these leaders. Like you need to follow people like Andrew Ng, people who have actually done research, rather than these people like who have left the tech world long ago. Yeah. So yeah, this was the article. Facebook shuts down AI chatbots as they create language humans can't understand. So these are all like very hyped up news. You shouldn't follow these. Okay. So what is actually feasible by current methods? So there are these four areas. Computer vision, where computer vision deals with how a computer sees an image. Like, computer sees an image for a computer is just a matrix, a 2D array of numbers. That's how computer sees any image as such. And then natural language processing, like I'm speaking words, you're able to infer meanings in your mind, right? Your mind does that to you. So how do we code it in a computer? Like, the best example would be your Google Assistant. Google back to you, right? So that is again deep learning there. And then speech. So you remember in 2009 or 10 when Apple first introduced Siri, right? It was pretty basic in what it could do and stuff. But today, if you see Google Assistant and compare it with the Google Now or OK Google from 3 years ago, one important change you can see is the Google Assistant of today can speak English in Indian accent, right? Have you noticed that it's not a robotic voice? It's not that Stephen Hawking voice that comes out anymore. It has that Indian accent in it. Advancement in speech. And then robotics is where the reinforcement learning, that's a very promising field as of today. So yeah, let's see the first one, that computer vision. Yeah. So this is a nice application. It's known as deep neural style transfer. How many of you have used Prisma, the app? I don't think anybody uses it anymore. It was popular, right? So this is what it does. So you have this Starry Nights painting by Van Gogh, and you have this dog, a photo of a dog. So it basically extracts the features, only the style from this image, and transfers it to this image. So this was the rage in say 2014 or 15, but it's a beaten problem now. Like anyone can do it. You have your computer, you can just go to the GitHub repo, download and run it on your photos. So this was in 2014. So this is not exactly cutting edge, but this kind of changed the understanding of computer vision, because we thought we were thinking, okay, we can maybe extract edges, we can maybe extract, some, let's say if this is a dog, we can extract the nose and stuff, but it is able to extract the style like our mind does. Like in your mind, if you look at this Starry Night photograph, and you can superimpose it on anything, and you can imagine, right? You can imagine, let's say Vidhan Sauda in that style. Your mind can do it, right? But mathematically encoding it, neural networks are able to do. So this is one of the advancements. Okay, object localization. So all of you have heard about simple classification techniques, right? Like let's say I take a picture of a dog and it says it's a dog. So that's a well-beaten problem in deep learning. Like it's 2018 now, and it can identify almost anything as of now. So the difficult problem though is, given a picture like this, you have to localize and say, okay, this part here is a dog, this part here is a person, this is a skateboard, and this is a chair. So this is known as the object localization problem. And even this, like you have like more than 10 to 20 state-of-the-art methods which have uh, which have actually beaten humans. So basically they had this data set and they asked humans to classify and localize objects, not a simple image like this, maybe tougher ones. And when they took the average scores of humans versus the neural network, the neural network actually beat humans by a few average points. So object localization is one of the very important problem. And if you want to look at the use cases, like for example, uh, I'm working on such a use case. Like I'm working on the union governments. They announced this smart city project. Remember, right? So they're putting up cameras all over, and this basically gives you in the camera feed. If you look at it, this basically gives, okay, these many autos, these many altos, these many SUVs have passed by, and these many people have passed by in this road. And basically, if you have a camera feed for, let's say, a 3 kilometer junction, and you have 10 cameras, you can track the same vehicle across the city wherever it goes. So yeah, there is also the fear that it might be used for surveillance and stuff. But yeah, there is always pros and cons for technology. So object localization is one of the most important applications. Then we have, yeah, segmentation. So once again, going back to what I told, how a computer sees an image, right? It's two-dimensional, right? So the photo is two-dimensional. You don't know the depth information. Suppose, like I take a photo, and so suppose if you look at this photo, you don't know if uh, this guy here is like probably 10 feet tall, and the background might be smaller. But since you're a human, okay, the average height of human, you can say, okay, the buildings are tall. But how will a computer know the depth information from an image? So that's where semantic segmentation comes in. So this is a type of neural network that says, okay, this is your foreground, this is your background, and you have to focus on the foreground first. And you have to focus on the foreground first and then the background. So this is like very important because this is what driverless cars use. I mean, this image is taken from Uber driverless car. Like this is how it sees the world. Like it sees this guy in red, like all the people in red and cars in blue, and the background and the sides in green. So that it means it needs to focus on the road and not hit this person, not hit the cars, not hit the person, not hit the cars, and then it has to correct its path so that it goes to its destination. So yeah, semantic segmentation is one other very important area. Yeah, so face recognition has been there from decades, but when you apply neural networks to face recognition, we have almost hit 100% in face recognition. Like, I mean, Apple just introduced Face ID in their new phones, right? There's no fingerprint and stuff. And even Android is planning to roll out Face ID next year. So one important application I would like to say is, sadly, it's being used for surveillance. Like in China, it has been deployed like at a massive scale. Like all the policemen have a device, and it just scans the gives where they're walking at. In fact, I think I have a demo. This has been implemented for India as well in Coimbatore by the company I was working for previously, Hyperverge. So yeah, YouTube works. I can show that to you. Okay. If it is here or one video in the website, I'll just see. Okay, I think I'll go to the website and show it from there. Yeah, it's deployed in Coimbatore city. So as you can see, it detects all the faces, right? So in any video stream, any face will be detected, and yeah. So you see these people here, right? These three people. It says Victor, Vadivelu, and Khader. So these three people, like they're in the criminal database the police maintains. They're like past offenders or people who are out on bail or something. So their information, their photos is already stored in the database, and that is fed to the neural network. And wherever they go in the city, they will be tracked. So like he can go anywhere, any surveillance footage, he'll be tracked. So yeah, this has good use in the sense you can track criminals wherever they go, but the government can also track anyone they want, right? So that's one of the downsides. Yeah. So the application that generated, the most views or the most hype and like everyone was excited was generative networks. So till now, what we saw, it was basically you give data and you ask the neural network what to do. Like you ask it to identify a dog in an image, or you ask it, to say segment out the foreground, the background, or you ask it to recognize a face. But generative networks, on the other hand, the neural network itself generates like it itself generates art as such, art, music. It generates videos on its own. So here you can see this image here, right? This is an original photo of zebras, and you ask the neural network to put horses on it. It can do that. Like in the same image, the zebras are converted to horses, and again the reverse here. For a horse, for each horse you put a zebra. And if you look at this, paintings can be converted into realistic looking photos. Like for the human eye, you cannot differentiate if it's a painting or a photo. And the reverse also, from photo you make it into a painting. So generative networks are like probably the most promising things in the future, because that's where the questions of creativity of an AI exist. Whether AI is able to do something or not. But the thing is, as of now, it's very good on computer vision part, on like images. And if you look at the music generated, I wouldn't call it music. As of now, it's just noise. It can't really generate music that well. But yeah. So yeah, it can do this. You have a photo of smiling woman. You subtract it with photo of neutral woman. You add it with a neutral man. You get a smiling man. These are like conceptual mathematics. Like you have man with glasses, you subtract man without glasses, so that should essentially say, okay, it's extracting only glasses, information of glasses, and you add a woman without glasses, it puts the glasses on the woman. Yeah. So stack GAN, GANs are basically generative networks. So stack generative network, it converts text to image. So this is where the creativity of humans versus the AI came into question. Like this paper literally broke the internet. So you can just describe anything to the network. Like you say a small yellow bird with a black crown and a short black pointed beak. So you see in the first, it creates this. So yeah, it takes concepts from the sentence you give, right? Like yellow bird. First it identifies a bird, then it remembers how a bird looks like, then it extracts the color information from them, and then it goes for the specific details you mentioned. So yeah, stack GANs is one of the most promising applications. Oh, so cycle GAN is one other another
Hi.
form of. So like, don't worry about the names. These guys tend to keep weird names.
Can you hear me?
So how many of you play this new game called PUBG? A lot of people play, I guess, right? Yeah. So basically, PUBG is let's say a realistic version of another game, a very similar game called Fortnite. Fortnite is only for PS and PC, and in Fortnite, it's basically a fantasy world. You have 47s and stuff like that. So one guy, what he did was he trained a network so that would, even if you're playing Fortnite, it will give the look and feel of the entire world like PUBG. You can see here the transfer has occurred, right? Like uh, the textures, everything from this world has been transferred to that world. So this is again one other generative network which does this. Okay, so this was about the the basic and the most eye-grabbing innovations from the field of computer vision. One other field which has been completely revolutionized is natural language processing. So deep learning has completely revolutionized. However, NLP was like, I mean, 10 years ago, you couldn't imagine that you'd have something as advanced as Google Assistant. But today, Google Assistant can talk like a human. It almost passes the Turing test. So yeah. So word to vec. So word to vec is basically like for each word you have a numerical representation of it. Okay? For every word in the English language, or how many ever words you train it for, it has a numerical representation. And from that number, and if you see, this is completely unsupervised. Okay, like you don't tell the you don't tell the network, say, okay, in my language, say father and mother are related. You know, father, mother, son. These are words which you would associate closely, right? I mean, you know it because you know the language. But when you give it to the network, it learns that association on its own. And you can do this. Like you can say, you can take the numbers, the vector that for the word queen, subtract it with king, and add the vector of a man, you will get woman. Very similar to what we saw in GANs. You subtract the concept, and you can also like, it need not be this. You can just put Hindi also, like say Raja, Rani. It still works. Like let me show it to you. Like, so there is this thing called fast text by Facebook AI Research. They have already done it for say 200 languages. So you need not even train, actually. They've used all the data in Wikipedia, and they have trained it for you. You just need to conceptually, if you want, you can just download this and you can try it on your own. So it's available for Hindi, Tamil, Kannada, any language as such. So yeah, Facebook AIs, it's known as fast text. So yeah, I'll be coming back to word to vec when I go deeper into neural networks and stuff. But yeah, and sentiment analysis. How many of you have heard of it? This is like the number one go-to buzzword, because I don't know, they've been doing it for many years with many other methods. Like you have many other. I mean, if you want to think about it, the simplest way, the most basic way to do sentiment analysis would be to have a list of positive words, to have a list of negative words, and count the number of positive words, negative words, subtract it, and say, oh, okay, give the score. This is like the most basic thing to do. But you can easily beat such technique. You can say not happy, it will still count it as positive, right? So for such things, you have specialized neural networks that take care of it. They learn the nuances of the language, how it is, and all of these things, they use the word to vectors, which I mentioned in the previous slide. Because neural networks, essentially, they cannot take in words, they cannot take in images directly, right? They cannot take a JPEG. As I said, the image is a matrix of numbers. You feed numbers, it spits you numbers. For words also, you need numbers. You need to represent the word in some numerical format. So that numerical format is the word to vec. Okay, you give in a number, you give in a number, it spits out another number, and that number is your sentiment score, right? Yeah. So visual question and answering. So this is like a combination of NLP and computer vision techniques. So you just have an image, you ask questions about the image, and it gives you answers. Just looking at what's the image. So here you can see what is the mustache made of. It identifies the banana there. It see it. The neural network shouldn't just know what a banana looks like. It should know what a banana looks like, and it should know what a mustache is. It should know where a mustache is in a person's face, and then relate that to the question that is asked, and then answer. So you see, the process is like, it's not very straightforward, right? Yeah. So machine translation. So even this has been there since the 60s. And people have been doing it in various ways. But one thing you can realize is translating between any two languages. If you just translate it word by word, it'll be horrible, right? I mean, that was Google Translate in, let's say, 10 years back. Remember, if you do Hindi to English or English to Hindi, it would be terrible because it would do word by word translation and the entire meaning is lost. So that's where again neural networks come into picture. Like, I mean, I don't know how many of you have used this. Google Assistant can talk to you in Hindi as well. Has anyone tried it? Like, I mean, if you want, you can try it now. You can just ask it to like open Google Assistant and say, talk to me in Hindi, type, talk to me in Hindi. It can converse in Hindi. And also Google Pixel 2, the new phone, they have a special, I mean, it's only for their phones they release this. Like if someone is, say, talking to you in Spanish, they do a real-time translation of that. Like real-time translation of Spanish to English, and whatever you speak, it's real-time translated to Spanish and given back to them. So yeah, machine translation is one other very important area where neural networks are applied. Yeah. So reading comprehension. This is a very hard problem. Like even with neural networks, it's a very hard problem. So what is reading comprehension is, right? I'll give you a Wikipedia article. Let's say I'll give you a Wikipedia article of Mahatma Gandhi. You'll read through it. I'll ask you questions on it. So you'll be able to fairly answer, right? Like if I ask you, or not even answer, let's say I ask you when was Mahatma Gandhi born? Don't just answer. Just highlight the part of the article which has this information. So I'm even simplifying the problem even more. You need not even answer in your own words. Just highlight that part. So even doing that for a machine is a very hard problem. Like people have tried so many things until this neural networks came out. So they kind of encode the entire article in a mathematical representation. So when you ask a question, it points out where the answer is. I mean, this has already been implemented in certain things. Like if you Google sometimes, if you Google something very specific, sometimes it actually brings out a Wikipedia article and highlights the part that is relevant, right? So that is again reading comprehension in play. Yeah, abstractive text summarization. So how many of you use InShots, the news app? I think a lot of people use InShots. So there's one other app for news called Awesomely. Anyone uses that? Okay. So yeah, so InShots is basically they actually have a team of people who sit and write news in 60 words. Whereas Awesomely is also by an Indian guy, and what that does is that actually summarizes it on its own. It kind of gets the news article and says, okay, these are important, I'll summarize it. But what those techniques do is, those techniques basically see, let's say you have 10 sentences in an article. It identifies the keywords in each sentence and ranks the keyword according to its relative importance or something. Let's say if the article is about the 2019 elections, it probably would give importance to sentences which mention Modi and which mention Rahul or someone. So from 10 sentences, let's say you want it only at 4 sentences, it'll just pick those 4 sentences and give it to you. That is normal summarization. It kind of makes sense when you read it because your mind can connect the dots, because okay, it's. But when you use neural network techniques, we are looking at something like abstractive text summarization. So you feed in the 10 sentences, it reads, it understands, and it writes on its own. Like here you can see the entire sentence is Russian Defense Minister Ivanov called Sunday for the creation of a joint front for combating global terrorism. It should say Russia calls for joint front against terrorism. So it kind of picks what it needs and generates a completely new sentence on its own. So this is what the future is like, abstractive text summarization, where the machine is able to read from huge paragraphs and generate its own interpretation, abstracts on its own. And yeah, so this is one more very important technique. So how many of you, has anyone worked on OCR stuff? Optical character recognition. It's been there for a very long time, right? I mean, people, about OCR, right? OCR. It's basically you have a text in an image. It converts that into text. If you take a photo of anything, and if there is any characters there, it converts it into your text format. So that until recently, until they used deep learning techniques, was the accuracies were very low. Actually, you couldn't do much work in it. But now with deep learning techniques, it has become very easy. Like OCR is almost a beaten problem, and the thing it works on any language. Like I don't know. Has anyone used this new feature in? I think what's the newest phone in Galaxy series? 9 or 8? S9, right? So S9 has this assistant known as Bixby. So it's by Google, but they have given it only for exclusively for S9. So it has this kind of something known as Bixby Vision. So what it does is, let's say there is something written, and you take a photo. It not only tells you it not only gives you the text, it can translate it to other language along with the same texture. Like it doesn't, and superimpose on your phone, like augmented reality. Like it just appears to you as if it has been translated, but the entire texture of the scene is the same. So that's where these modern OCR techniques come into picture. Yeah, and moving on to the third field which has been revolutionized, it's speech. So speech for decades. And how many, like, are there any electrical engineer people who studied electrical engineering here, electrical or electronics? Yeah, so you would have done work on speech, right? I mean, at least signal processing in general, right? So people have been using signal processing techniques for many years, and the accuracies were still not that great. Using signal processing techniques to identify, let's say, a simple problem like say identifying who is talking, it was fine. But when you see the impact of the neural networks from 2012 2013, when they started using that for speech, the accuracies have risen like anything. And currently the state of art speech recognition techniques can actually beat humans. Like there have been instances where they have 20 to 30 speakers speaking at the same time, and neural networks can learn to differentiate each one of them, which humans cannot do. Right? We have I think humans cannot do it beyond like 8 or 10 people. So speech recognition is one other field which has been revolutionized. And yeah, so speech synthesis is where speech synthesis is basically generation of speech. Like earlier what we were doing is whatever you say, it will be converted to text. It will be fed into an audio AI model, and that will generate uh, the response in text again, and that will be converted into speech using that you remember that monotonous robotic voice, right? That's what they say robots sound like, the monotonous voice. But with speech synthesis it has changed. Like wavenet it's already around you, it's already deployed. Like the Google Assistant uses wavenet. Yeah, you use the neural network that generates speech in, like, say, Indian accent, Spanish accent, and stuff like that. So speech synthesis is one field. And yeah, neural voice cloning. See if I have a demo for that. Okay. To the part where he explains, shows the demo. Okay, this is sad. So the audio. Okay, I mean, uh, oh, yeah. Uh, where is it coming? Okay, I don't think we can do this. So yeah, neural voice cloning, what it does is it takes speech samples of a person and then tries to replicate that. Basically you can, and the good thing about this is it doesn't need like lots of data. For example, if I have a 5-second clip of you talking, just 5 seconds, I can replicate your voice and make you say anything. So in a country like India, I think that's kind of dangerous if you think about it. So yeah, and the deep reinforcement learning. This video, but I don't know about the audio.
Board game. Okay. It's one of the simplest and also most
There's volume controls in this.
professional player is a long standing.
Oh, volume control. Yeah, HDMI takes in. How many of AlphaGo? I mean, how many of you have heard of this game called Go? Right, it's a very ancient Chinese game. It's kind of more complicated than chess. Like chess in itself has so many different possible moves, right? But the number of possible moves in Go exceeds the number of atoms in this universe. Like it's very exponential, right? So chess is kind of easy to code in. Like a computer, we beat the audio. Audio playing there.
Long-standing challenge of artificial intelligence.
Full.
Your system is value.
Huh?
System value is value.
Hmm?
System value.
System volume is full. Yeah, so we beat the best chess player Kasparov in 1997 itself. IBM's Blue Gene, if you remember that historic match. So chess was not let's say it was not a difficult problem to solve because of its limited moves. But Go, on the other hand, like since the number of moves is so huge, you would require you would require a network that is large enough to learn so there is this company called DeepMind in UK. So they were trying to solve this problem, and Google bought them. And, they together with Google devised this neural network known as AlphaGo. So what it did was, for a period of around 60 days or something, 40 to 60 days, it played games with itself. It played games with itself, like it it created like two players and started playing with itself. And from each game, it started learning, like, oh, okay, this is how it is. And they also feed in historic Go data. There is like World Go Championship and stuff like that. From those games, also, it started learning the strategies. It started learning how to play and stuff. But The one thing about the game Go is like, for example, in chess, if people have played, there are like certain openings. There are certain techniques that you would use. You know, like there is Gyoko piano. There is the French defense you would use. You say, okay, if the first move is he uses the C file, you would start probably use the Russian defense or something. But Go after a point of time, there are no techniques. It kind of becomes intuitive. You know, it kind of becomes the, okay, I know this person. So Go players not only study uh, the game, they also study the person. You know, like, okay, this he is such kind of person. He's likely to be aggressive at this juncture, so I would likely to make this move. So it's more intuitive in its sense, and the fact that AlphaGo actually beat the world #1 Go player, you know, the #1 player in Go from South Korea, says a lot about how the field has advanced, and they're actually launching a movie on it. I don't know if you can hear it, but I have subtitles or something.
Long-standing challenge of artificial intelligence. Everything we've ever tried in AI is everyone tried to get the number of possible configurations of all is more than the number of atoms in the universe. AlphaGo found a way to learn. So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Mr. Dog.
But looks like no other is about to get underway in South Korea.
You said all this to go when Roger Federer is and it's just the very thought of a machine like humans. The place is a madhouse. Welcome to the deep mind challenge. The whole world is watching. Can find AlphaGo's weakness? Whoa. Is there in fact a weakness? Turned on its axis. That is not constant base. It's developing into a very, very dangerous fight. All the Green is left around. Is about to cry. I think something went wrong. Yeah, it's made a mistake. It's got a possible here. These ideas are driving AlphaGo. We're going to drive our future. This is it, folks.
So yeah, they're making a movie out of it, a movie or a documentary out of the entire AlphaGo experience. And even in the trailer, when I put on captions, did you notice it was they have this new kind of captions, you know, the auto generate, right? Even that is a neural network there. Like it's just speech to text neural network. The ones we talked about previously. Yeah. So we come to the scary parts where it can have a wide impact. So I don't know if many of you are aware of this, but there was a huge social media circus about this thing called deep fake. It's 5 months ago or somewhere, in February or something. It came up on Reddit first, and then people picked it up. And since it was a very easy method to produce fake things, it became very huge. I think I have a video of it. So yeah, people started doing this with deep fake. So this is bad. Yeah. So you see, that's Nicolas Cage right there. They just replaced the actress with Nicolas Cage, and yeah, this was they were doing it for many films. I mean, Nicolas Cage was in Lawrence of Arabia. He was Indiana Jones. He was everywhere. So this started out as a joke, but think about it. It can have like wide impact, right? Like let me show you the next one. That is even more scary. Yeah. So deep lip sync. So can anyone identify which of, so I'd say one of this is original video of Obama talking, and the others are created, you know, synthetically generated. Can you identify which is original and which is not? Huh? It's a first one is original. Anyone else countering that? Huh? None of them is original. So
pixels per click. Because our approach requires only audio, we can generate a high quality.
So they just need audio, and they can generate Obama talking, And look at this.
Even with the original source video has low resolution.
So here in some of the frames, Obama is not actually visible, but the model is able to extrapolate and say how the facial expressions change. Like for some words, Obama uses, his facial expressions change. It's true for everyone, right? We speak in a certain way, and it has looked. They have actually trained it on I think some 120 videos of Obama from YouTube. That's it.
One of the skills that I bring to
So deep lip sync is one more application. The most scariest of all was this. It's a combination of audio and video. What we saw in the previous two. So in this, you can basically have anyone say anything. Like, have a look at this. Okay, there is no captions for this.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time. Even if they would never say those things.
Even the audio is generated here.
For instance, have me say things like, I don't know, Killmonger was right. Ben Carson is in the Central Place. Or, how about this simply, President Trump is a total complete. Now, see, I would never say these things. It's not a public address, but someone else would. Someone. Jordan.
You can see it was Jordan Peele who generated Obama saying the exact same thing.
Trusted sources. Now, basic, how we form information. I mean, the difference between whether we survive or whether we become some kind of fucked up dystopia. Right?
So imagine this in an Indian setting. I mean, in our country we have riots on WhatsApp forwards and for badly photoshopped images, and something like this, you can have a politician say a particular thing you want. You have inflammatory speech and you can circulate it, and that's pretty dangerous, right? So there are infinite uses, but it's basically like nuclear energy. You can either use it to generate electricity or bomb other countries. So yeah. Okay, so the math behind the magic. So how many of you are like Harry Potter fans? Have read all the books or watched the movies at least? No one? Yeah. So do you remember Harry Potter and the Prison of Azkaban? The third part. So basically, there is a monster called the Boggart. Yeah. So the Boggart in Harry Potter universe, it does not have any fixed physical shape. So to each viewer, it appears differently. So for each viewer, it appears as the most scariest thing for that person. So whatever is scary to you, it will look like that. And the way ridiculous and it appears very simple. So that's the thing with AI. When you're studying AI, you just trivialize it. You just bring it to the simplest bare bone mathematics, and you'll say, oh, that's all it's doing. Like, okay, that's why this is happening. So if you can break it down into math, it's actually very simple. So yeah, so essentially deep learning and AI, whatever we are doing today as of now, is just curve fitting on steroids. It's exactly like a linear regression or a simple classifier, right? What you do in a simple classifier is you let's say you have 4 points, you have to separate into 2 and 2. You just draw a line and say this 2 is one class, this 2 is other class. So deep learning is exactly the same, but on a higher dimension. Right? So look at this data point on the left. Okay, so you have these green dots, you have these red dots, and you your task is to draw a boundary such that you can differentiate green and red. For this task, you build a neural network. And what it essentially does is, so it basically keeps transferring this into a very higher dimension. In the first layer, it maybe looks like this, it looks like this in the higher dimension. And then the next phase, it looks like this. When you keep moving, you realize it's coming very closer. And in the highest dimension of what that particular neural network you have designed can do, it look like this. Like it look like a straight line. And here you can just say, okay, in this straight line, here is where I mark, right? Here is the differentiate, whatever you need to differentiate, right? So this is what a neural network essentially does. Like, okay, suppose you have, let's say, circles on this side and dots, dots or some other shape on the other side. And let's say you want to classify these things, you want to say, given any point, given a new. So what you would do is you would maybe draw a line, here, and the equation of the line, right? It's simple coordinate geometry. You have the equation of the line, and given any new point, you would say probably calculate the distance of that. I'd say I put a new point here. You calculate the distance from this line, which and say if it is this side, this is a circle. If it is this side, it's a dot. So the exact same thing. If it is something like this, let's say you have circles. And you have points all around it, okay? So in this case, you cannot draw a line at all, right? There is no one line, like you cannot call this line and say, I'll classify, like, I'll have like a 20% accuracy in this. So this is not an acceptable solution. So what you do, so this is in 2 dimensions, right? Now imagine this figure in 3 dimensions. So all of these will be floating around, right? Like the dots are floating around like this. And on top of that, you have an elevated kind of structure where you have the circles, right? So if you imagine in 3 dimension, here between this circles and between these dots, you can draw a line, or you can have a plane, because in 2 dimensions it's a plane. And then you say, okay, I have this plane now, give me any point, I'll do it. So this is what neural networks actually do. Like they just map it into a very high dimension. I mean, we humans can only visualize 3D, right? You cannot, it takes it to like 10th dimension, 100th dimension, and says, there I'm able to separate the data. So that's what it essentially boils down to. It finds the dimension where it can separate the data using a line, or whatever the equivalent of a line is in that dimension. So yeah. So before we start, like, it's good if you have a basic understanding of linear algebra for neural networks, at least. So what you would need is a basic understanding of linear algebra. I don't say too much basic, basic to intermediate level of linear algebra, and then a little bit of calculus is what you need to understand it completely. Okay, so I should use the board or something. Get it there. Okay, so in computer science, you know what an array is, right? An array of numbers, right? You just have this. So this is an array of numbers, right? So a vector in linear algebra, it can mean different things to different people. A vector for a physicist is different, for a mathematician is different, for a computer science guy it's different. So for computer science and mathematics purpose, we just say vector is just a list of numbers. For computer science, it's just any list of numbers, any one-dimensional array. You can call it a vector. But when it comes to mathematics part of it, so you have to first define what is known as a matrix. I mean, you would have studied, right? A matrix is just, again, if you want the computer science term, it's just a 2D array of numbers, right? So say you have a matrix. So you have a matrix, and this is of the order, you have 2 rows and 3 columns. So we call it 2 cross 3 matrix, right? So when a matrix has only rows and it has only 1 column, it is generalized as a vector. Like so this is a 3 cross 1, right? This is 3 cross 1. They don't call this a matrix, they call it a 3 cross 1 vector. So this is the mathematical notation of a vector, one-dimensional array of numbers in matrix notation is known as a vector. And then you have something known as the tensor. So tensor is nothing but it's an n-dimensional matrix. Let's say you have let's say you have this matrix, right? You have 2 rows and 3 columns. Now I do into 2. That means there is one more matrix of 2 cross 3, any value, right? So you basically imagine this, like first you have this, then behind that you have this, okay? Like imagine it in a 3-dimensional space. So you have 2 cross 3 cross 2, right? So you have okay, this 2 comes in the front, yeah, this 2 cross 2 cross 3. So you have 2 matrices of 2 cross 3 each. So that's the notation we use. And this generalization of a matrix in many dimensions is called a tensor. So in deep learning, you'll be you'll be using tensors a lot, because an image, even though it is 2-dimensional for us, it is not a matrix, it's a tensor, because so each number will represent 1 pixel, right? 1 pixel, and each pixel is not just 1 number. It is not like 1 or 2. Each pixel has 3 numbers, because it's a color image, right? So you have RGB values. So it is, each pixel has 1, 2, and 3. So an image will be having, so if you have a 15 cross 15 image, a 2-dimensional image, when a computer sees it, it will be 3 cross 15 cross 15. Because you'll have 3 matrices, 1 for red, 1 for green, 1 for blue. When you stack it up all together, it becomes your complete image. So that's like the basics. You have any doubts in this? This is kind of important. Vectors, because it's very relatable, I guess, because all of you have used arrays and matrices in computer science. It's exactly the same, and that's how we use it. Like, any doubts on arrays? Yeah, see, I just wanted to introduce you to terms, because you can say tensor and get away with anything. Mathematical terms, a single column matrix is known as a vector. That's it. Like, basically everything in the world is tensors. Okay, anything can be n-dimensional. So you have a 2D matrix that is n-dimensional. It's tensor. You just have a 2D structure. That's a matrix. You have it in 1 dimension, just a single column. That's a vector. So tensor is like the absolute generalization of everything. So how many of you are like familiar with Python? So one other thing with machine learning as a thing is, since there is too much mathematics involved, what they've done is, and since Python is a kind of, it's a very easy language to pick up, and it's very easy to code, because there are many layers of abstraction within itself. All the current frameworks, all the tools you need to develop neural networks, everything is in Python. So understanding of Python is kind of necessary when it comes to neural networks. So NumPy is a package in Python which helps you to manipulate between vectors and stuff like that. So I generated a random 3x3 matrix. So visible, right? Like the now, huh? Oh, you cannot see the numbers. Okay, okay. Okay, so there are few basic matrix operations. I don't know if you have heard of it. So there is this something known as the transpose of a matrix. Okay? So if you observe closely, you can see. So what the transpose operation has done is all the rows have been made into columns. All the columns have been made into rows. So you can see 0.92, 0.83, and 0.48. Here is the row. Here it has become the column. So we'll be using like transpose a lot. So that's like a very basic operation. And so one other important operation in matrices is known as matrix multiplication. So how do you multiply two lists of numbers? So that's where this matrix multiplication comes in. So yeah, and when it comes to matrix multiplications, there are certain rules you have to abide by. So for example, here, what is the dimension of this? A is 3x3, right? B is also 3x3, and you can multiply them. You can multiply two matrices provided the second dimension of the first matrix and the first dimension of the second matrix are the same. So if I change this to 4, it will say error. Yeah, it's not aligned. But the second column of the second matrix can be anything, and can be anything. Wait, I'll just make it into 3. So we are multiplying a 3x3 matrix with a 3. This and this needs to be the same, and the resultant matrix will be 3x12. The remaining two numbers. So yeah, you have a 3x12 matrix. Yeah, so you matrix from that multiplication of those two matrices. So that is one. Okay, inverse is not required as of now, so I'll be skipping it. Yeah, so more to this concept known as supervised learning. So what exactly a neural network does is, so the most basic form of teaching a neural network how to see patterns is you provide it with examples. Okay, you give a photo of a dog and you also provide the label saying it is dog, because it can't learn on its own. You say dog and you give the label as dog, and you provide, let's say, 1,000 images of dogs with the label dog. You give 1,000 images of cats with the label cat. Only then it is able to map. It can learn and it can map, saying, okay, given any other image, this is a dog or this is a cat. Yeah, so it's talking about supervised learning, right? So supervised learning is it's basically like this. You have your raw data and you feed it to the network along with the labels, and the entire process of learning is known as training a network. So you basically ask the network to learn all the patterns in whatever data you have given, and finally when you push it to production, it should work on any given data with a reasonably a pretty good accuracy. So supervised learning is just like that. Okay, so the humble perceptron, the first, you can say, one of the first learning based methods was known as perceptron. It came out way back in the 1950s. Like even in this, you could feed in examples and ask it to learn patterns, and it basically has to predict given any other pattern. So this is how a perceptron looks. Okay. Yeah, we represent perceptron by a single circle as such, and all the inputs are lines like this, lines with arrows. This is how we represent inputs. So suppose, let's take the simplest case. You have two inputs. I'll call them x1. I'll call the other one as x2. And for each of these lines, we have something known as the weights. You have w2. So because see, these are the inputs which you give, and you also give what comes out of this. That is the output. So you give x1, x2. Those are the two inputs, and you give the single output that is expected out of the algorithm. So what the algorithm learns, how does it learn, is it basically tries to adjust these two values. W1 and W2 are adjusted and learned such that for any given x1 and x2, the desired output is whatever you are given. So how does it do? So for example, in mathematics, let's say you have 5 tables. Okay. So if I do this, so what's the answer? Like, it's 5 times something is 15. Instantly you can fill up 3, right? So suppose we don't have that information. So how would you start? So what we would do is we'd randomly select a number. Let's say we will start with 2. Okay. And we'll say, okay, what is 5? Then we'll compute what is 5 cross 2 is 10. Okay. Is 15 like is 10 positive or negative? It's positive. So we'll add, we will increment in a small number. Okay. We'll and that small number is pre-computed. We'll say, okay, the small number is 0.2. Okay. So we'll make, instead of 2, we'll make it 2.2. Okay. We'll do 5 into 2.2. We'll get something. Then we'll know which that is greater than 10. So we're moving closer towards the answer, right? Then we'll do 2.4. Then we'll do 2.6. Ultimately, we'll hit 3.
So this is supervised.
Yes, this is also a form of supervised learning. We know our output. We have our input. You're finding whatever is inside.
So how decide that?
Which one?
These things, it depends on your like cofactor. It's affect your
Okay.
output. So how to decide that?
I didn't get your question still.
Suppose my profit is 50. I'm expecting 50 my profit. So what I need to look at is, so I need to reduce my cost or something, the cofactor.
So you basically say what needs to be put into the image, right? What needs to be fed into the network? What kind of features? So that again is like, there are many methods. Like it will always obviously be good if you can select. For example, let's take simple prediction, like something like cancer prediction or something. In that, what all? So you have records of parameters. You have their readings, and in that, from that, you have to predict whether they have cancer or not. So in that case, let's say I give you, I'm the hospital manager, I give you data that will include some one column in that Excel is probably patient ID. Yeah.
It's an outcome basically. So daily basis, doctor will give you an outcome. So your health is increasing.
Yeah.
So based on that, you have to decide. So you can face in future cancer or not. So that kind of things.
No, this I'm talking about definite prediction. So in such a case, in such when you give an Excel which has patient ID or something, that is definitely not helpful. That definitely won't impact, right? So in such cases, it's better for the human to sit and say, okay, these are the features which impact. So even in sales of a company, it's the profit, the sales, or the inflow of cash. These are the things which impact my final profit, and feed only those to the network. So it's usually better in case, but in some cases you have like too many data points and you're not able to decide what to put. You can feed everything into the network, of course, by removing obvious ones like patient number and all. You feed in everything, the network can actually learn to ignore certain features. Like say, if you actually put 2 million records of cancer patients along with the patient IDs also, it will eventually learn, oh, okay, the patient ID is not at all impacting my final outcome. So it will learn to ignore that also. It all depends on how smartly you also do it. So AI doesn't mean it's, everything is in the hand of the computer. It's mostly in our hands how we design the system. So you understand, like this is what learning means, right? So just imagine that in terms of the perceptron here. You give an X, you give Y. It has to learn these W's that impact. So how is this W's calculated is, so whenever you give X1 and X2, internally it does this. It does W1 into X1 plus W2 into X2 will give you some value. Let me call it H. Yeah, you can think of it like that. So to obtain, so this perceptron also has something known as the activation function. Okay? So it behaves just like the neuron in your brain. So this number H, right? Because in the end, what a perceptron gives out is just 0 or 1. Okay? So you decide on a threshold. You say if H is a positive number, the output is always, you give out a 1. If H is a negative number, you give out a 0. So this is how the entire process works. Like whatever you feed in, it is multiplied by the weights, and a function is applied, an activation function. In this case, it's known as normal step function. So you say if it is positive, give 1. If it is negative, give 0. And this is compared with the actual Y you want. So for example, let's say you want to learn the AND function. Remember AND, right? 0, 0, 1. So these are our inputs, and the output of AND is 0, 0, 0. Only the last one is 1, right? So you want to make the perceptron learn, fit to this, such that when you just give 1, 0, it should give 0. When you give 1, 1, it should give 1. So in this, what you do is you have the perceptron, you have X1, you have X2, you have W1, W2. So earlier in that example, we used like 2 cross slash equal to 15. We randomly selected it to be 2, right? 5 cross 2. We randomly, so even here, you randomly assign some value to W1 and W2. It can be anything. It can be 0.5, minus 0.3, anything. Okay. So you have randomly assigned the system, and so for the first one, for the second example, you give 0 here, you give 1 here. So you calculate W1 X1 plus W2 X2. You will get some positive or negative value, right? And based on that, you put 1 or you put 0, right? So suppose if it comes correctly, if the expected value is 1 and you also get 1, everything is fine. But if your expected value is 0 and you give a 1, then you have to update your weights, right? Like here we did, right? We increase it by 0.2 or we decrease it by 0.2. So that is where we have something known as the update equation of a perceptron. Yeah. So your weight, you have to add. So R is basically the learning rate. Okay. So in that example I told 0.2, right? You increment in 0.2. So you fix R here in this equation, you fix R as 0.2, 0.3, and then you basically whatever output you get, you subtract it from whatever is required, and then multiply it with the input you have provided. So this is basically saying how much of a correction you have to make. See, you shouldn't make it like since okay. So here, suppose you want to get a 1 for 0 1, you have to get a 0, right? But you predict 1, and you change it completely such that it'll provide 0 for this example. But you shouldn't change it to such a drastic extent, because there is one more example below. You have 1 0 and it should produce 0 for that as well, right? And you have the same weights for all the examples. So you have to change it in such a way that the change is reflected only for this example and it doesn't affect the others. So overall, your aim is to find weights such that it generalizes across all the given examples. You need not hit 100% accuracy. I mean, here, since it's a simple example, you'll hit 100. You can generate all these given inputs, but in a very complex situation, even if you can adjust your weight such that 90% of cases are fine, 95%, even that's a pretty good metric. So yeah, show the code execution of perceptron, how it looks. So there is this library called sklearn or scikit-learn that implements most of the standard ML packages, but I don't think we'll be using that. So, yeah. So these are all the various packages you have to use. And this was the activation function I was talking about. So you can see if x is less than 0, it gives you 0. Else, if it is greater than, if it is a positive number, it gives you 1. Okay. So this is a pretty simple function there. And this is my training data, as you can see. So we are learning the AND function, right? So you have x1, you have x2, and you have w1, and you have w2. So here we do w1 into x1, w2 into x2, and to get an output, right? But let's say both the inputs are 0 and 0. Everything will be gone. Like you cannot update the weights. It'll always be 0. Suppose I have some other table where I want 0 0 and it's 1. It is not possible to arrive at this number, right? Because everything is 0 0. So what in machine learning, what we usually do is we add one more extra term. Okay, it's known as the bias. So what it does is it provides, it's a constant one. It's always 1. So regardless of the other inputs, so there's one small w3 here. Regardless of other inputs, you just don't want to make the network 0, because anything multiplied by 0 is always 0. So you put 0 inputs. There is at least one positive input to give you something out of the network. Even if everything is gone, all your data is bad, you have something that gives you some output. So here in the code, you can actually see here. Yeah. So this is x1. So each row is represented there. So you see, this is x1, this is x2, and this is the bias. Bias is constant 1 throughout all the 4 examples. You can see the AND gate there, right? You see 0 0 0, 0 1 is also 0, 1 0 is also 0. Only 1 and 1 is 1. So this is my entire training data, right? Like I'll say this particular block is x, and this is my y. I'll be taking them out in a for loop. Okay, and these are the weights. Okay, I've initialized 3 weights, and this is my the learning rate I told you, right? 0.2 or 0.3. Very incremental changes you have to do. Okay, so here is the main algorithm of your perceptron. Okay, so for each of the training example, I take the x value. I take what is the expected value, that is y. So I take this entire thing and this, and then so if you can see, this is actually a vector, right? So we represent it as a vector. So go back to this one. So instead of doing this w1 x1 plus w2 x2, so the reason why linear algebra becomes important here is, here you can see if you want to implement this is fine, right? I mean, you can code it, but let's say you have 1,000,000 points and you have 1,000,000 weights. So the for loop, what it would do is you have to wait for, it's basically O of n, right? You have to wait for 1,000,000 iterations to finish, and you have to sum it up, and you have multiplication in between. So this is where we represent it as made, the vector notation. So I have a vector like this. I have one more vector like this. So this is 1 cross 2, right? You have one row, you have two columns. This is 2 cross 1. You have two rows, you have one column. So you can multiply these, right? Because this and this are same. And in the end, you get a 1 cross 1. So when you multiply this, what exactly, like what this 1 cross 1 number is, it's basically w1 x1 plus w2 x2. The advantage here though is, since it is vectorized, things go parallel. Like you don't have to wait for, when you do it serial, you have to do this first, then this first. But here, this multiplication and this multiplication happens parallelly, and then they're summed together. So that's why this is faster, and we use the vector multiplication here. And then, yeah, so once you get the result, you calculate the error. Okay, if there is any error, like what is the expected value, and this multiplication, you put that activation function. You say basically, if it is positive, you put it as 1. If it is negative, you put it as 0, and you subtract the difference. And this entire line is that update equation I showed you, right? This, you're updating the weights in each, and then this plots the error. If I'm not wrong. Yeah. So you can see the error, like how it was. It should predict a 0. It predicted -1. It should predict a 0, -1. Then it should have predicted 1, but it predicted 0. So it oscillates over. Yeah. So after like 65 iterations, you can see it achieved 100%. Like there is no point in training anymore because it has achieved 100%. So you can see here, for 0, 0, it gives minus 0.6, which is 0, which is negative number. For 0, 1 also it gives negative number, which is 0. For 0, 1, 0. For 1, 1, it gives a positive number, which is mapped to 1. And these three are the weights. See, we started with a very random weights, and we ended up with these three values, right? So now if you plot that in a graph, it look like this. So here is your 0, 0. Here is your 0, 1. Here is your 1, 0, and here is your 1, 1. So only 1, 1 is a separate class because the output is 1. For all this, the output is 0. So basically, you get a line from the weights. You get a line that that separates it into two classes. And how you get the line is also pretty simple. So finally, you have this W, which is learned, right? This is the final weights, which I showed you here. These final three weights. I mean, x3 is just 1. Remember that, okay? So if you look at this equation closely, when you're plotting it, x1 and x2 actually are the xy coordinates, right? When you say 0, 0, 0, 0 is here, 0, 1 is here, 1, 1 is here, and 1, 0 is here, right? So 0, comma 0 corresponds to coordinates 0, 0, 0, 1. So if you consider x7 and x2 as the x coordinate and the y coordinate value, if you go back to your high school mathematics, this closely resembles this. Anyone remembers this? equation? This is the equation of a straight line, right? So this W3 X3 is a constant because there is no variable because X3 is 1 always. So yeah, constant. Yeah, constant one. So C is your constant here. X2 is your Y coordinate and X1 is your X coordinate. So ultimately what you get by learning those W's is a line, is one single line which can separate the given values into two classes. Okay. And the same thing going back like, so this entire thing is known as a perceptron. But so this was introduced in 1957. It's like way back, like this is a very standard thing which existed from those times. But if you want to see the limitations of a perceptron, you can do this. So this is the XOR gate. No? If it is 0, 1, it is 1. If it is 1, 0, it is 1. Otherwise, it's 0. So this is how the XOR is defined. So let's see what happens to XOR. You can see here for the AND there was conversion, right? Like the error became 0 at the end, but here it did not, because the perceptron cannot divide XOR function. Like it cannot learn it at all. Wait, so what happens is so you have 0, 0, you have 0, 1, you have 1, 1, and you have 1, 0, and so 0, 0 and 1, 1 are one class. Okay, and 0, 1 and 1, 0 are other class. So you have to draw a line to separate these two from these two. Like, is it even possible here? No, right? I mean, you cannot draw a straight line anywhere. You cannot draw this doesn't work, this doesn't work. Like you have to get these two on one side and these two on the other side, right? So this is not possible by a normal perceptron. So this is where the limitation occurs. But imagine you build a neural network. Remember I told you putting this into higher dimensions and stuff like that. Imagine the same scenario in 3D. It becomes a very simple problem. You can, like these both are in some 3D space, this is in some 3D space. You can easily draw a plane like this which separates both of them, right? So that is where the need for neural networks arise. And so people just started out with the perceptron, and the basic concept of a neural network is very similar to perceptron, except in perceptron you have this one unit which takes in inputs x1, x2. It has a w, it multiplies w1 into x1, w2 into x2, sums them up, and then says if it is positive 1, negative 0. But what a neural network is basically, you have many such units. Okay, this is not only one. You have many such units, and you have it in depth also, and all of them are connected. And remember, each of the connection has its own weight. Okay, it's connected like this. So each of the neuron is connected to everything. So this kind of resembles our nervous system in the brain. That's why it's known as the neural network. And so this is one change that they did. Instead of having a single unit, they had multiple units and multiple layers of multiple units. And the second change that they did was they changed the function. Okay. So this function here, it just tells you, it just gives you 0 and 1, right? This step activation function. They changed the function into something else. So yeah, this is like the representation of neural net. So you can see each node is connected to every other node, and it's stacked up also. So they changed the function into something known as the sigmoid function. Okay. So what this does is, so the sigmoid function somewhat looks like 1 by 1 plus power minus x given. Yeah, it might look complicated, but so what it basically does is, given any x value, you say f of 2, you give f of 10, you give f of 100, it just fits all the values between 0 and 1. So the graph of sigmoid looks something like this. This is 1 and this is 0. So any value, and this is like 0.5. So any value, any large value, it squashes its value between 0 and 1 and gives you the equivalent. Okay. So suppose you have 1 to 1000, 1 might be very near to 0, 1000 might be near to 1. So you'll get a value between this. So why this is important is because sigmoid value gives you the kind of it's somewhat relative to probability. Yeah? Like in the end, if you put this, it can say, so a neural network, what it does is, it doesn't definitely say given a picture of dog or cat is dog or cat. It says this is 0.7, 70% sure this is a dog, 30% sure it's a cat, this is a cat. So that's where you say, okay, you pick the largest and say, okay, dog is what it's most likely to be a dog. So for that 0.7, 0.3 difference, you need to use a function like this. You cannot use a binary because the learning itself, you cannot be so sure, right? Even humans sometimes miss it. So that's where you use an activation function like sigmoid, which gives the value, it's continuous. It's between 0 and 1, you get a value. Yeah. So that's the basic difference is the activation function for sure, because there you are using the step function. That in a perceptron you use a step function, like, so you have x1 x2, you do w1 x1 plus w2 x2, whatever you get, you say if it is greater than 0, that is 1, if it is less than 0, that is 0, right? So here what you do is you calculate this, the same thing, w1 x1 plus w2 x2, whatever value, let's say you get h, right? You feed it to the sigmoid function, okay? And that value is taken forward, like so if you say this is the input node, this is like x1, you have w1 here, this neuron gets values from this all these neurons, right? It does the same thing, w1 x1 multiplies the weights by the inputs, sums it up, and then instead of putting the perceptron's step function, it applies this sigmoid function, and you get a value between 0 and 1. Yeah? And that value is then passed on as the input to the next one. So this is an iterative process. So this guy takes it from this, the same thing. You have weights here also. Yeah? And finally, in the output layer also, you take all this, and here again you put one more sigmoid, and you get a value between 0 and 1. Yeah, yeah, yeah. So for dog and cat, this won't work. Like you need to have, instead of 1 here, you'll have one more circle here. Okay. So that will also have connections from these. So one of the neuron is responsible for saying dog, the other is responsible for saying cat. So each of them, after application of sigmoid, will give you a value between 0 and 1. Suppose the dog neuron gives you 0.7, this one will give you 0.3. So you know, okay, the probability of having a dog is more, so you would go with that neuron. Yeah, so that is so that's what people generally tend to use. Instead of having separate neurons, they have a single neuron, but they modify the sigmoid function. So currently what you saw, this sigmoid function, it takes in a number and gives you a number between 0 and 1, right? So they modify this such that it takes in an entire vector, okay, a vector of numbers, and gives a vector of output, all of them between 0 and 1. Okay. So in the dog cat example, it takes in this entire vector and gives you a 2 cross 1 vector, basically saying it has two values. Okay. It says 0.7 and 0.3. That means the first value is 0.7 is dog and 0.3 is cat. And in such cases, you have to make sure that the sum of the vector is 1, because probability can't exceed 1. So, yeah. You have some other activation functions also, like something known as the tan h. Even this looks very similar to sigmoid, except the range is between -1 to 1. So this is tan hyperbolic. And one other very important thing that came out in the late 2000s was they started using the simple function known as ReLU. Okay, all it does is max of 0, 0, 0, your number. So you give 10, it just gives output 10. You give -1, it gives 0. Okay, so people say in training neural networks, right? So the current practice is what they do is they put this sigmoid function only in the last layer, because that's where you need the probability values, right? And in all these middle layers, instead of using sigmoid, they use the ReLU function. So that's like the standard method as of now. So, but it doesn't matter. You can use sigmoid, you can use tan h, any method that gives you a non-linear approach. It doesn't give you a binary value. Between 0 and 1, any function that gives you that, you can use it. So yeah, this as I told, so yeah, you can see here you have two inputs, okay, and these are the weights as we saw in the perceptron, but this is like you have many layers here. So this is known as the input layer. Okay, the input layer is also represented by a node. This is the input layer. Whatever input you give, this is the hidden layer, and this is your output layer. And any arrow means there is a weight associated with it. Okay, so the weights are randomly initialized in the beginning, and you say you have your input, you multiply. So to calculate whatever to calculate this hidden value, you basically do this times this plus this times this, you get a value, and then you put that into the sigmoid function, and whatever output you get is this layer's input to the next one. Okay, so this entire process is known as forward propagation in neural networks. It's exactly the same thing as what was there in the perceptron, right? You just multiply the things by weights, only the activation function changes in neural networks. That's it. So once you draw it out and you do it, it's pretty clear. It's pretty easy. Yeah. So ReLU's performance is better in hidden layers. If you use instead of sigmoid, it solves. There are some problems known as vanishing gradient problem and stuff like that. It tries to solve such problems. So the performance is better, and it learns quickly with ReLU instead of sigmoid. So that is there. Yeah. So one more important change in neural networks with respect to the simple perceptron is how you update your weights. There it was simply you take the difference between the input, difference between the output and the expected output, multiply it with your whatever input value you are given, and you update the weights based on that, right? Based on a small based on a small rate. Okay? Here also it's similar. But so what happens is, so let's say you have a function y equal x square. Many of you know this, right? This is a simple parabola, right? Y equal x square. So what is the minimum point in this? Is x equal to 0 is when is minimum. So imagine the loss you're going to take. So whatever is expected minus whatever you got, right? Whatever result you got. This you need to express this in a function, right? So one of the most famous loss functions that we use is known as mean square error, right? So what you would just do it, you just subtract this, you put, so this becomes the mean square error between what is expected and your whatever output you have got. So even, so this last function, whatever you design, right, it can be mean square or it can be some logarithmic based methods and all. I won't go into that. So this loss is also essentially a function, right? And a simple mean square will be somewhat like this, like, no, somewhat like this, because it's essentially a parabola, and this is your minimum point. Okay, this is the point where the error is the lowest. So if you plot this, so this factor is known as error, right? So you're basically doing error square by 2. So you'll get a parabola, and you have to find that point where error is lowest, and that means you have solved the problem. So how do you go about is, when you randomly initialize a weight, okay, you will be, the error will be high, right? If y-axis is your error, the error will be very high because it's random. The network doesn't know anything, right? And basically, you imagine this as a ball, okay, and you have to move towards this point. You have to roll down the ball down the surface of the loss. Okay? So this is where the weight update comes in. So in neural networks, we update the weights using this equation. So what it does is, this is known as gradient based approach. So for example, in, let's say 10th standard physics, you would have learned that what is velocity? Velocity is basically rate of change of motion, right? So you remember this equation, dx by dt. So change in motion with respect to time is velocity. Or when you differentiate, it says how much the velocity is affected by this time factor, right? So the weight equation is something like the new weight equal to old weight minus some eta. This is the, again, the learning rate we had seen, no, in perceptron 0.2, 0.3 or something that you have fixed, into, you differentiate the error with respect to the weight. Okay, so this is rate of change of error with respect to the weight. Just like you have rate of change of motion with respect to time, will give you how much the velocity changes when you change the time, right? Here what you need is how much the error changes when you change the weight. So you update it accordingly such that so in every iteration, when, so if you start in the error surface here, you slightly update, you come here, okay, and then you come here, and then you come here, then finally you reach the point, you reach the minimum point, like, yeah. So here you start out from here and you finally reach the minimum loss. Huh? You cannot say, because it's error, it can be anything, like when you're training very deep, very large nets, right, it can be like 7,000, 8,000, but the neural network is quick to learn, like 7,000, 8,000, within 3 iterations it drops down to 300, 400, maybe like for the next 10 iterations it comes to 100, and in the last few iterations it'll be, if your network everything is proper, it'll probably drop to 0.5, 0.6. So error can be anything, it's a huge graph. So you start from here, but you'll end up, like, you have to end up in this region, like, so this entire method is known as gradient descent. Okay, so, and this is the update. So like, why you do this is basically you are calculating how much my error is affected by my weights, and you adjust accordingly. So this is the change, you're subtract. Okay, so this minus sign is because this change can be negative or positive. Okay, so if it is positive, that means this is a little abstract concept, but yeah, so you don't So we have this graph here, right? It says you have to move in this direction. But when you're training a network, it doesn't know, you don't have graph, you don't have human supervision to say, yo, okay, you're here, you move here. It might be here. And if it moves here, you're gone, right? So this gradient also gives you which direction to move. If you have to move towards this or you have to move towards this, okay? So, I mean, if you need not think this, but if you remember slopes from coordinate geometry, right? Slope of a function. So when you take a slope of finding the minima of a function, right? When you take it, when you differentiate, and if it is greater than 0, you have to move this way. You have to, if it is less than 0, move this way. So that's the exact concept here. So that's why you have this negative sign. If this is negative, this becomes plus. If this is plus, this remains negative. So it's the opposite direction you have to move. And that's where the minima lies. So this entire thing is here. But again, so this is a very simplified loss we're looking at. This exactly won't be the case because this is a two-dimensional thing, right? I mean, this is for a single weight, two-dimensional thing. Imagine you have a multi-dimensional thing. So in that case, imagine a bowl, okay? Like imagine a three-dimensional bowl, and this will be your minima. And the thing here is, you can see there is, unlike this y equal x square, when you can say pinpoint and say this point is my minima. In most real world scenarios, you won't have a global minima. It will always be some local place where you see, okay, error is 97%, but I cannot move forward, okay, and you stop. So that is there, and it need not be a bowl structure also. It can be like this, you know. If your loss is like this, you cannot say if this is lower or this is lower. Either one of them is an acceptable solution, right? If you guys say if this gives 96.5, this gives 97, it doesn't really matter, right? Yeah. So you have any doubt in gradient descent? Like this is like very basic, one of the basic algorithms in neural network. Any doubt? Like conceptually, at least you understood, right? Leave the math behind. You can understand the concept, right? Like you have weights, you have error, you have to hit the one way, you have to adjust the weights accordingly so that you hit the minimum error. So that's what neural network is all about. Adjusting the weights so that your final error is the lowest. Any doubts on this? The error rate, you fix it manually. So what people generally do is when they start the training, right? When they start, they put alpha as 0.2, 0.3. You know, they have pretty large learning rate. But as the network progresses, they decrease it. So that once you are near, so what happens is, see, this slide. If you have a very large learning rate, if that alpha is like 10, 20, this will happen. It will get the multiplier. Instead of having this alpha is to be small, it will make, if it is large, it will do this. Instead of incrementally, you know, slowly moving towards a target, if it is 0.2, it will move here. If it is 10, it will just jump here. Again 10, it will jump here. So you will never reach your goal. So the alpha parameter or the learning rate parameter should be as small as possible. Like 0.2 or 0.3 is the agreeable limits. Okay? So yeah, so this update, right, gradient thing, whatever we are doing here, if you look at a network, how many weights are there? Here you have 1, 2, 3, 4, 5. There are so many weights, right? And you have to do it for each one of them. Okay? You have to do the propagation for each one of them, and it's not that simple. Like you cannot say, okay, I'll take this weight, I'll do differentiate error with respect to this weight, and then adjust it. Okay, here you can do for this particular branch. Okay? But when you go back to here, you can also see, but this weight depends on this weight, right? Because what you're doing is you're taking this input, multiplying this by weight, doing it for this neuron. So this neuron's input, whatever this neuron is taking this as input, is in fact an output of all the previous ones. So this weight not only depends on this, but it depends on these weights, it depends on these weights up until the input. So that's where we use the chain rule of differentiation. Like it is like little advanced, but it's fine. So basically, this W represents the entire weight ecosystem. Okay, just learn that way. Like the weights have to be propagated backwards such that you update this means you have to update everything. Like if you're updating the one in the layers 2, that means you have to update in layer 1 as well, because layer 2 is dependent on layer 1. So the dependency need to be maintained. So the method of how you update the weights in the final algorithm is known as the back propagation algorithm. That was introduced in the 8th. Yeah. So we won't be going into details of the back propagation algorithm, but remember this. So forward propagation is just multiplying the weights with respect to the input and putting an activation function, right? So you have you randomly initialize weights, you have inputs, multiply, put an activation function. If you put a simple step function saying +1, -0, that becomes a perceptron. If you put a sigma function and say I'll give you a continuous value between 0 and 1, that becomes a neural network. And you have many such networks, and you multiply each of the weights and stuff like that. That becomes an entire, layered neural network. Okay? So yeah, so in programming terms, so you know what a loss function, right? I told you. So this mean square error, what we call, like what is expected value, you subtract it with what you got, and you take the whole square of it. That's known as mean square error. Likewise, you have some cross entropy error and stuff like that, which is more suitable for image problems and stuff. So basically, what you need is you have inputs, you have weights, and you have a loss function. Okay, these are the things we have to define when building your own neural network. And then optimizer. Optimizer is basically this small part, right? So optimizer, how you update the weights. Okay, so this is like the basic method. There are some other methods. They introduce some other parameter, to basically make it learn very faster. So that entire part is known as the optimizer. So it acts on this loss function. Okay. And there are 3 more terms. So these are like, so whatever data you get, right, you split it into 2, usually 2 or sometimes 3 parts, known as, one is the training data, the other is known as testing data. So the training data is what you feed it to the network, okay, and you update the weights. But okay, you update the weights, and once you feel it's performing reasonably well on the training data, like let's say you put 1000 images of 500 images of cats, 500 images of dogs, and you have 100 images of dogs and 100 images of cats set aside. Okay, you won't touch it for now, and you train your network such a way it can recognize, let's say, out of the given 1000 examples, it can say recognize 995 of them perfectly. Okay, that's like a 95% accuracy, which is pretty good. And then that is not your final accuracy metric. Okay? You take the network, you keep the weights, all those things as it is, and then you feed in the 100, 200, the 200 images you have set aside. On that, you don't update the weights. You just calculate. Okay, even if it says dog is a cat or cat is a dog, you're fine. You say, okay, that is an error. And in that, let's say if it is out of 200, it says it gives you only 4 images as wrong results, and rest are, which is 98% accuracy. So that is your final metric. Okay, so that is train, test, split. And validation data is usually what they do is while training, they sometimes they usually don't train the entire thing. So in our dogs and cats example, I told 1000 images is what you're training, right? 500 cats, 500 dogs. In that also, they take 100 aside. Okay, 100 aside, 50 dog, 50 cat, and after each iteration of training, once you go through all the 1000 images, all the 900 images now, okay, then you calculate what's the accuracy on the remaining 100. You will get some very bad accuracy in the first iteration. Then you feed the network the same dogs and cats again. Okay, second iteration. Now you test it on this 100 images. The accuracy should have increased because it is seeing them twice. The weights are adjusting. Okay, the accuracy has increased on this 100. You keep doing this for a fixed number of iterations, and you should see the data on this 100 at least increase. So this is known as validation data. I mean, if you have less data, you need not have a validation data. You can just use the test data there to, see if it is increasing on the test data, and then say, okay, we have a reasonable accuracy measure.
So this training data set, we are taking the training population. It's like suppose there are 1,000 dogs and cats. It's a group. So I want to take 100 of from that 1,000. So how to decide? I don't know if that 100 can be only cat, that 100 can only dog. How to decide that?
So you already have labeled data, right? Because labeled data is essential. Like you know which image is dog, which image is cat. Like you'll probably put it in one folder say dog, one folder say cat. So you know it's 500 of dogs, 500 of cat. And when you feed it to the network, you're feeding the Y value, right? Even in a perceptron, you say, you give input dog, you say this is a dog. Give input cat, you say it is a cat. So that is very important. Like the label data is what we are working here. Okay? And yeah, so how to implement? Oh, okay. Yeah, Epoch is basically like one complete iteration. So you have 1000 examples. You go through all the 1000 examples. Okay, that completes one epoch. You go through them again, second epoch. So you do this for like 20, 30 epochs. You go through all the examples again and again and again on the training data, not on the testing. Testing is always separate. You go like 20 times, 30 times the neural network. You feed the same data again and again. The weights are updated. Okay? And after 30 or 40 epochs, you feel okay, it's learned. It has learned something because you can test it on the test data. I mean, what people usually do is they train it for accuracy is 57%. They go back, they train it again more, they come back. It should have increased. Otherwise, there is some problem. Maybe the learning rate you have to modify, all these parameters you have to modify and then train again. Okay? So this is like a complete iterative process. So Epoch is just that. And how do you implement? So all the current deep learning frameworks, that gives you access to these neural networks, they're all in Python. Okay? There are two major frameworks. One is TensorFlow by Google, and the other one is called PyTorch by Facebook. TensorFlow is what the industries use in production level and stuff like that. Okay? Because it's very optimized for production systems and stuff. And TensorFlow is a little difficult to code because it is not how we are used to programming. Because TensorFlow is basically you create a graph. Okay, when you say you create that neural network, right? You create a graph. You create nodes. You create edges. You create weights. And that graph is whatever you write in Python, it is compiled to C++ and kept in the backend. So whenever the data comes, it basically flows the tensor. Like so, you remember the tensor, the definition, right? Basically, n-dimensional matrix. An image, whatever you give it as a tensor, and you have this graph defined. So it basically flows the tensor through the various operations, like maybe matrix multiplication to multiply the weights. Then you add something, and then you put the activation function. So that's why it's known as TensorFlow. Okay, but PyTorch on the other hand is designed for easy use. Like anyone can. It's designed such that it's basically you create a class of a neural network, and you say I want this layer, I want this layer. It works. So it's very object oriented. It's human readable, but unfortunately PyTorch is not production scalable. So you can write models, and you have to port it to some other framework for it to work. But TensorFlow, once you write, it's painstaking to write, but once you write, it works. So to make TensorFlow easier to code, one independent guy, he created another framework called Keras in Python. So Keras, you cannot do it on your CPUs. So that's where the bottleneck comes. Like even if you have a 8 GB RAM, 12 GB RAM machine, the memory taken is too much, because if you see the network here, each of these arrows is a weight, and for each of this weight you have to compute the differentiation with respect to the error. So I mean, for a typical neural network, the parameters are in millions. Like for a simple, let's say, remember that object localization example, right? That given a scene, it says this is a person, that is a dog, that is a chair. That network has 2.3 billion parameters. 2.3 billion parameters which have to be calculated, which have to be changed, and stuff like that. So that's where the limitations of CPUs occur, and that's why you have NVIDIA GPUs. So that's where what they do is, since every operation that we discussed is converted into vectors and matrices, right? So any multiplication, any addition is done in the form of matrix and vector format. Like we saw in perceptron, right? The weights W1 x1 plus W2 x2 is done via a vector addition, right? I showed you. So you do this W1 W2 and you have this x1 x2, and then you multiply. So this, for the GPUs, are very optimized piece of hardware, which is very good for such vector and matrix multiplication. So it's very fast. Like if you look at 1050s, the basic gaming gaming, even they offer almost 40 to 50 times faster computation when compared to your laptop CPUs. So that's where, so NVIDIA becomes a very important part of deep learning. Like how many of you have an NVIDIA GPU in your laptop? Or okay, the thing is, AMD doesn't work. It has to be NVIDIA, because all these frameworks are built around. So NVIDIA basically came up with a new language called CUDA. Okay? So what CUDA allows you is, it's basically written like it's in. You can just include it in C++. CUDA library. What it does is it allows you to access the GPU memory. You have 12 GB RAM, but GPU also has 12 GB, 24 GB variants. It gives you access to that memory. So all the Python frameworks I told you, right? PyTorch, TensorFlow. Inside, they call these CUDA functions to access GPU memory. So they send your matrix, whatever you define, to the GPU directly, so it can, the computation is faster. That's why NVIDIA becomes a very essential partner of deep learning. And if you don't have, it's fine. So what you can do is, you use Azure, right? People use Azure, AWS. So all of these services, if you just sign up, they give you, AWS gives you $100. $100 is at least 50 hours of GPU. So if you want to train something, you just create a free account of AWS. In that $100 you can use. And Google Cloud gives you $300 free credits. Again, they can give you GPUs. And there is this really nice thing that Google launched. How many of you are aware of it? So it's known as Google Colab. Okay, this type Colab Google, collab.research.google. So they give a Python notebook kind of thing, so where you can write your code, and for 12 hours, for up to 12 hours, they give you a K80 GPU, NVIDIA K80 GPU for you for free. Like you can do all the training you want for free on this platform. And if you look at the price of K80s, I think it's more than 1 lakh or something. It's a very costly GPU with huge RAM and memory. So, yeah. So Colab Google does this. So they solve one of those problems. So, yeah. So I have a demo of small neural network in Keras. So there is this very famous data set, MNIST. Okay, so it's basically handwritten digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have these digits written and a photograph of them is taken. Okay? And this data set was created way back in the 80s. So we'll build a neural network that will learn to classify each of them when given a digit. Okay. So yeah, and we'll be using Keras for this. So these are all the necessary imports and stuff. So you have 10 classes, and the epoch is like I'm doing it for 20 epochs here. So so just to give you an idea of how the image will be, this is an image, and this is a very simple. There is this image is not a tensor; it's a matrix because this is a black and white image. Okay? So here you will have some number, and this is 28 cross 28. So each image is the same size. They have made sure that. Okay. So you have 28 cross 28 image, and you are building a neural network. So you have one more layer here, and then you have an output thing. Okay? All of these are connected. So these are the inputs, right? So how would you give an image as an input to a neural network? Right? So here what we do is this 28 cross 28 image, right? We flatten it out. So 28 into 28 is what? 784. Okay? So you have to basically when you say 28 cross 28 matrix, you have 784 values inside, right? So we create 784 such input nodes, and for each node you feed in each number. Let's say this one number goes here, this one goes to the next one. Get it right? So that's how you feed the input to this neural network. And so you have 6,000 training examples. Sorry, 60,000 training examples of these digits with their corresponding labels, and 10,000 are my test samples. Okay. So, yeah, this is how an image looks like. This is the 28 cross 28 thing. This is apparently 9. Let's see a different one. Okay, this is a 3 here. I'm randomly choosing, and okay, this is 0. Okay, so you see this is how the entire image looks. Okay, and this is the 28 cross 28. So in each of this you have one value. So 0 0 so you 1 2 3 4 5 6 28. Next row you have 29 to another multiple 56, and it goes on until you have 784 values, and all of these you feed it to the neural network, right? Okay. So this is that. Wait. So we are building. So you have 784 input nodes, okay, and each of them is connected to. I have 512 here. Okay? So these architectural constraints. Okay, so this is where humans come. So regardless of what the AI learns and all, you have to provide the correct architecture for it to learn. So I provide 512 here and one more layer of 512. So basically this 512, each node in this 512 stack takes input from each of these 784, and then it passes on to each of these in 512, and then finally you have 10 nodes because you have 10 classes, right? Each of them spits out the probability of that number being belonging to that class. Okay? So this is the design of the entire network, and in Keras you can do it in 6 lines. This is all you need. You say model is sequential. You say so. These kind of neural networks which I'm talking is the basic kind of, it's known as dense neural networks, because every node is connected to every other node in the next one, right? So you say dense, let's say 512, and the input shape is 784. So input is 784, and I want 512 nodes. Okay. Dropout is a higher level concept. You just have it here. You don't think about it. Okay. And then the next, so you say input is 784, you have 512 nodes, and the next one is also 512 nodes. Okay. And then the last one depends on the number of classes. Number of classes is 10 here. Okay. So let's build the network. So this is done. The network is built, and the summary gives you, what is the input shape, what is the output shape coming out, and see, even for such a simple network, you have 669,706 parameters which have to be learned. Okay. And this will increase exponentially if you have I told you, right, for tasks such as object detection and stuff like that, it's in billions. The parameters are in billions, and you cannot run it. That's one of the limitations of deep learning as of today. Like something like as simple as linear regression, you can do it on your phone, right? Your phone is powerful enough to do such computation. But something like this requires you to be connected to a cloud server, which, cloud GPU server, which can run and give you an API call, which can give you this, right? So that's one of the limitations. So one of the things which you can expect in the future is like it's a very upcoming thing. Like deep learning has been there from 4 or 5 years, but one of the very upcoming thing is actually more powerful. It's a combination of deep learning with blockchain. So what they're trying to do is, so this training, for example, I need a very huge GPU to do it, right? People don't have access to compute. So the GPUs are in the hands of this powerful company. Like, for example, what Google can do, Google can train a huge network with huge, they have data, they compete with them, right? Like if you want to compete with Google, if you want to create a product that competes with them, you cannot do that. It's out of the question. So they are so when you put things on the block, what they're trying to put on the blockchain is the compute. So basically, I have my phone, you have billions of phones, right? So if you have a neural net and you can distribute the computation, okay, so this function here is what you have to finish. You have to say, you have to put in your training values. Okay, x train is the input, y train is the labels to the input, saying what digit this is. Okay, 0, 1, 2, 9, and epochs is we have specified how many, 20 epochs. Okay, we'll do it for 20 epochs, and you also put you also give the testing value, right? So let's start training it. So you see, this is a K80 GPU. This is so fast. 600,000 parameters. I mean, my laptop is a 4 GB machine. It usually hangs. Cannot take in this compute. So this is the thing with neural networks. Once you start training, you just wait. That's causing a lot of conflict with HR people, apparently. People just put neural networks on training and don't do work. So you can see here the loss is initially 0.24, it's 0.1, it's 0.07, 0.05. So it's reducing, right? So that means, okay, in that gradient thing, we are going down, we are going towards a minimal value. So here, the job of a computer vision engineer or a deep learning engineer is to whatever data you get. See, in the real world, when you're solving real problems, there are no data sets. So the company usually gets data from somewhere. There'll be some people, or they give it to some agency where they annotate the data, say the labels, all those things. So your job basically comes down to getting the data right, putting it into the right format. That is one thing. And the second is designing the neural network, like the architecture, right? I told 512, 512. You can drive it 512 to 56, things like that. But recently, like 1 month back, there was a paper by Google Research, which is known as AutoML. Okay? They have a thing called architecture search. So it basically searches for the best architecture and uses it. Like So all you have to do for that thing is you have to give the training data, and that's it. It will search the best architecture, it will train the architecture, and give you the output. So yeah, also, so yeah, it looks like it is trained. Let's code it. So yeah, you have a test accuracy of 98.37, which is agreeable, I guess. Plot the error functions, and over time you can see. Yeah, so you can see the training loss, how it has decreased over the epochs, right? So, the loss was very high when you started out, but then you can see it has decreased, and it has reached some level here. And even the accuracy. So when you're measuring accuracy, you should be a little careful, because I told you about the validation or the test data set, right? The accuracy is always with respect to that. So you can see the blue line is the train accuracy. The train accuracy is very high. It's well above 99, but the validation is not that much. It's like 98ish. So so you have to. So whenever you have a model that has 100% train accuracy, you shouldn't trust that. It is very comfortable with the training data, but it won't perform well over the testing data. That shouldn't happen, because your whatever model you're training, it is for real world, right? So it should generalize over examples it has never seen before. Like, the training is just to make sure it knows how a dog looks like. But looking at any street dog, it should say it's a dog. That you cannot have all the images of all dogs as your training set, right? So when you have 100% training accuracy, that's the validation accuracy is bound to suffer. So what people usually do is they usually stop somewhere here, and say, okay, this is a reasonably good test accuracy. The best test accuracy is where they stop the training and say, okay, let's take this model and use it. So yeah, that's it, I guess. Any questions you have? Simple manipulations. Like, one of the few things is NumPy is very essential. Like, see, first of all, Python as a language, and in Python the library NumPy, because you'll be using it because everything is vectors and matrices here. So NumPy, it's also very simple to use NumPy. And one more library is for tabular data. Have you heard of this library called Pandas? So you have this language called R, right? People using it. I mean, for 2-3 years back, it was really good, really well. Everyone was asking for R professionals. But this library called Pandas in Python, it basically copied all the functionalities of R and gave it to you as a package. So you need not learn a new language. You can just use any functionality of R inside Pandas. So if you know that one framework, that is very helpful in tabular data. And for image manipulation, when you're working with image data, OpenCV is good enough. Like, you do not know everything in OpenCV. Simple, let's say, reading an image, writing an image, resizing an image, because many times most of the networks will require you to have the image to be a fixed size. So you have to resize the given image to that size. All those image manipulations you would need. And apart from that, if you know the maths, also you can. I mean, if you actually look at the Keras framework, like, you can, whatever I told you about perceptron, how the weights update, you don't need any of that, right? You just need how to put the input. You have the architecture, you can code it in. That is enough. Like, mostly people use Keras in production, like, because internally it uses TensorFlow. You can use this in production and stuff. But again, when you are looking for a career in deep learning, the only thing people will ask in interviews and stuff is the math behind it. Because if you know the math behind it, they know you can do anything, any sort of manipulations